Good day, viewers. This is 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next exam. Moving straight into things, it's about time we talk about the fast approaching physics practical for WAEC 2024. What exactly is our question going to look like for this year? Of course, you're going to be given 3 questions. The first question is going to be on mechanics, more specifically on relative density. The second question is going to be on optics, and then the third question is going to be on electricity, this time around making use of a meter bridge. So what exactly should we expect? What should our question look like? Looking at things on your screen, our tool here is going to, for question 1, our tool here is going to involve a retort stand, a spring balance, beaker, water, masses, liquid labeled L, and then other necessary materials. So looking at these materials, which is going to be made available to you in the course of the exam, what question should we be expecting? Okay, this is more about upthrust, talking about loss in weight of a body when immersed in a different liquid, this time around talking about water, and then an unknown liquid labeled L, both liquid placed in a beaker. As you can see popping up on your screen, we have a probable question. The question says, study the diagrams above and use them as guides in carrying out the following instructions. Talking about the diagram, it talks about the retort stand, which is the support. We then have a spring balance attached or on the support, and of course masses is now being lowered into the liquid in a beaker. Of course, when we weigh a liquid in air, it's going to weigh more than when the liquid is being weighed in a liquid. Of course, the term here is upthrust, or what we call loss in weight of a body when immersed in a liquid. Okay, the instruction says, using the spring balance provided, determine the weight of object of mass M, which is 50 gram in air. Record this weight as W1. Of course, for any mass that we are given, the mass here talks about 50 gram. For any mass we are given, we have to first of all convert it into kilogram. How do we convert from gram to kilogram? That's going to be 50 divided by 1,000, and here that is going to mean 0.05 kg. We all know in physics that weight equals to mass times acceleration due to gravity. Weight is a force, so the mass here is going to be 0.05 times 10, and that's going to give us 0.5 Newton. So when we say 50 gram and when we say 0.5 Newton, we mean the same thing. So if you look at the instruction there, it says determine the weight. We were given mass 50 gram in air. We were told to record this weight as W1. So let us say for this question, as you'll see in the instruction, we were given one of the masses 50 gram, and then we were given another mass 100 gram, and then another mass is 150 gram, and then another mass 200 gram, and then another mass 250 gram. Each of these masses will now be lowered into water and into the corresponding liquid labeled L. Okay, first and foremost, the masses we are going to be given. Now, the masses for this exam might be different from these figures here, but one thing is already clear, that the weight you're going to have in air is definitely going to be more than the weight of these masses when lowered into water, and it's going to be more, the weight in air is going to be more than when it is lowered into a liquid. So dealing with the 50 gram here, we're going to get 0.5 Newton. You can see the unit is already there. To make this into decimal place, it's going to look this way. If it is 100 gram, you have to first of all convert to kilogram, and then you multiply by the mass in kilogram by 10, so that you get your answer in Newton. So dealing with 50 to 250 gram, if we are to convert that into weight of the masses in air in Newton, this is what we're going to have: 0.51 Newton, 1.50 Newton, 2 Newton, and 2.50 Newton. When these various masses is lowered into water and their weight read on a spring balance, recall that your spring balance works on the principle of Hooke's law of elasticity, and of course from the spring balance it is going to read in Newton. When this is lowered, the masses from experiment that we are going to have for the masses, the weights we are going to have for the masses is definitely going to be lower than 0.50. So when the masses is lowered into water and the weight read on the spring balance, we have 0.43, telling you that there is a loss in weight. This is the weight in air, this is the weight in water, this is the weight in air, this is the weight in water. So what that means is that the body or the mass here had experienced an upthrust. When the weight is lowered into the liquid labeled L in a beaker, this is the mass that we have. Of course, also, a decrease in the weight. There is a loss of weight, which we call upthrust here. So that ends that. So this is what we have for the table. So this just looks exactly like what you're going to be told to carry out in the lab for this exam. Then looking at the instructions that we have there, it says determine the weight of the object when it is completely immersed in water contained in a beaker as shown in the diagram above. Record the weight as W2. W2 is in Newton. We've done that. Determine the weight of the object when it is completely immersed in liquid labeled L. Record the weight as W3. We've done that. You can see in both cases, when in water and when the mass is lowered into the liquid, the readings on the spring balance, that's the weight as read on the spring balance, is definitely less, telling you that there is a loss in weight, that the body had experienced an upthrust here. Okay, that ends that. Then for Roman figure 4, we were told to evaluate U, which is W1 minus W2. We're told to evaluate U equals to W1 minus W2. W1 here talks about the weight in air. W2 talks about the weight in water. What we are looking at here is simply upthrusts in water. Upthrust in water. So when we say W1 minus W2, this is looking like 0.07 Newton. That is the loss in weight. So 0.07 Newton, that's the loss in weight. That's the upthrust in water. Upthrust in water is 0.07 up to 0.35 Newton. That's the loss in weight. Also, we're told to evaluate V. V here is W1 minus W3. In this regard, we are looking at what is the loss in weight when the mass is lowered into the beaker containing the liquid labeled L. So 0.50 minus 0.45, that gives us 0.05. So when we look at the difference between the weight in air, W1, and the weight in the liquid, W3, that is talking about upthrust in the given liquid L. This is what we have for V, and that ends that. So what other instruction were we told to? We were told to repeat the procedure with the object of masses M equals to 100 gram. You can see 100 gram, 150 gram, 200 gram, and of course 250 gram. In each case, evaluate U, which is the upthrust in water, that's W1 minus W2, and V, which is W1 minus W3. That's upthrust in the liquid. We were told to tabulate our readings, which we've actually done here. And we were told to plot a graph with V on the vertical axis and U on the horizontal axis. V on the vertical axis and U on the horizontal. V on the vertical axis and U on the horizontal axis. This we were told to plot, to which we shall now direct our attention. So moving on, we were told to plot a graph of V on the vertical axis as against U on the horizontal axis. So the very first thing you do when you want to plot your graph is to get your title down. After that, the next thing you want to begin to look at is how you are going to draw your vertical and horizontal axis, and of course get the scale in place, or being mindful of the right unit. In this particular question, when I want to draw for my vertical axis, what do you need as a student? You need your pencil and you need your ruler. I have mine here, okay? So you look at your V, it's to be on the vertical axis. What is the smallest figure that you have? This is the smallest here, and this looks like the highest. So 0.05 to 0.30. So I'm going to go to my graph book. For whatever graph book we are using, you should ensure that your graph that you're going to draw covers at least 70-75% of the entire graph book. Okay, so looking at this, the smallest is 0.05 and the largest figure here is about 0.30 Newton. So how am I going to go about that? If I take this to mean my zero origin, and I'm looking at, okay, on your graph book from here to here is about 2 centimeters. So if I look at this, so if I decide that 2 centimeter, that makes that 4 centimeter. 4 centimeter to represent 0.05. This would be 0.05, 0.10. That's not going to be enough. So I'd rather go this way. 2 centimeter to represent 0.05, 0.05, 0.10, 0.15, 0.20, 0.25, 0.30. But for your paper graph, on your paper graph, in an instance like this, you should be using, where I am using for my vertical axis, where I am using 2 centimeter here to represent 0.05, you should be on a paper graph, because of the size, you should be going 4 centimeter to represent 0.05 Newton. That's what you should be doing. So I haven't decided that okay, this is 0.0, 0.05, 0.10, 0.15, 0.20, 0.25, 0.30 from here to here. That at least covers a bulk of the graph here. So I'm going to go with my vertical line, no broken lines. You must ensure a well sharpened pencil, okay, and I'm going to go straight up, and here we go. I have my vertical axis already. Okay, let me just complete this. So there you go, there you have it. So I'm plotting a graph of V. So this is going to be my V in Newton. Okay, this is my zero origin, so this is going to mean, okay, what I have here is 0.10, and then what I have here is going to be 0.15, and this is going to be 0.20, 0.25, and then this is going to be 0.30, 0.35 of Newton. Of course, all that we need is for us to just stop at 0.30. So that just answers that for the vertical axis. For the horizontal axis, I have from 0.07 to 0.35. So I might just follow the same pattern here. In drawing my horizontal line, I also have to be careful, avoid broken lines, avoid stepping out of the thick line. That's why I must ensure a well-sharpened pencil. In this case, I am using a marker, and there you have it. So I haven't done this now. Okay, this is going to represent my U in Newton, so that this here is going to be 0. You look at the smallest figure, 0.07. So I might just start this as 0.05. This is going to be 0.10. This is going to be 0.15. This is going to be 0.20. And then this is going to be 0.25. And then this is going to be 0.30. And then this is going to be 0.35 Newton. And that's just about complete. The moment we are through with that, don't forget, we still have to write out our scale. So in writing out our scale, for my V, on my V axis, for my V in Newton, I am going to write as I have here 2 centimeter to represent 0.05 Newton. 2 centimeter to represent 0.05 Newton. On my U axis, that's the horizontal axis, I have 2 centimeter to also represent 0.05 Newton. That way, I have been able to write my scale out there on the edge. So what do I have now? I have to try and take out my plottings. When V is 0.05, this is 0.05 here. My U is 0.07, and that explains why you need to know what each of the O's represent. If I look at the fact that I have 10 O, this is 0.05, 1 to 0.06, 1 to 0.07, 1 to 0.08, 1 to 0.09, and then 1 to 0.10. So saying 0.07, if I am to mark that, that's this point here. Of course, when you get any markings, on your graph, you have to look for a way to clean that up at the end of things. So you're looking at 0.05 and 0.07, you pick out that point. Okay, that is this point. I've been able to do that. Okay, the next one is 0.10 and 0.12. This is 0. For my vertical axis, 0.12. This is 0.10. This is 11. And then this is going to be 12. 0.12 and 0.10. So that looks exactly here. You get that out as well. So that's how it's done. Yes. Then 0.17 and 0.20. For the vertical, 0.17. 0.17 here, this is 15. 1 to 16. 1 to 17. 17 is somewhere around there. 0.17 and 0.20. You want to trace that out. 0.20. Of course, that looks here. You've been able to do that. And then to the next one, 0.25 and 0.27. 0.25 here and 0.27. This is 25, 26, 27. 27 is exactly here. 0.25 and 0.27. And that just answers things. And then for the last one, you have 0.30 on the vertical axis. 0.30, this is 0.30. for the vertical axis, and on the horizontal axis that's 0.35. We need to get that out. Okay, that stops here, and that just talks about all of the points. So we've been able to pick our point for V, and we've been able to pick our point for U. So the next thing, as you can see on your screen, I haven't taken all the points, is we're told to determine the slope for this graph, otherwise known as gradient. So what we must ensure here is that at least 3 out of the 5 points are joins to form a straight line. In doing that, I'm going to try out this here looks out of point. Okay, let me see if I can match this 3. Okay, not really. Can I match this? Yes, I can. I got a point I can make use of here. So I got 3 points I can make use of here. So using my ruler, I'm just going to link those 3 points together, avoiding, of course, broken lines. Okay, now this is what we have. We've been able to join at least 3 of the points. So we are to determine the slope of this graph. Whenever we want to deal with slope, our slope here is always going to be change in the vertical axis divided by the change in the horizontal axis. This is our vertical axis. Okay, I'm going to come out this way. Okay, I'm going to try to pick good points. Okay, this here is going to be my change, delta V in Newton. This is going to be my change in the upthrust in the liquid, that's V. And this here, this is my horizontal axis. So I'm going to pick my horizontal point here. Just being careful so that you don't get the whole drawing scattered. This here is going to be my change in U, and that's also in Newton. So I just need to make extrapolations or sort of broken lines to get those points out. This here, okay, this way I get to this point, and this point here talks about my y1. So I've been able to get this point. This is 0.30. This is this, and then for the horizontal axis, I'm going to try to get my x1. This is more like my x1, and this here is going to be my x2. Looking at those points, this here, take note of that. This is like my x1. This is 0.07, 0.567, and this is 0.35. Take note of that. This here is 0.30, and then this here is 0.05, and that just about ends what we should have as far as the graph is concerned for now. So moving on to question IX, Roman figure 9, we're told to determine the slope S of the graph. Okay, the slope here is the same thing as gradient. You know, normally it's always y2 minus y1 over x2 minus x1. So from the plottings on the graph, this here is going to mean v2 minus v1, because our v is the horizontal, is the vertical axis here, divided by u2 minus u1. Looking at the figures we have from the table, this is going to mean 0.30 minus 0.05 all in Newton, divided by, in terms of U, we had 0.35, 0.35 minus 0.07 Newton. So computing this, Newton is going to take out this. This will mean 0.25 divided by 0.28. So computing that, we got 0.89, and this is not going to have any units because the Newton had cancelled out the units. Remember that this one is looking upthrust in the given liquid, more or less like upthrust divided by upthrust in water. So this is somewhat looking more like relative density. Have we been asked that question? Not yet, but the slope S is 0.89. Looking at the next question, question X, we were told to state 2 precautions taken to ensure accurate results. As you can see on your screen, these are precautions for this experiment and how you should record it, given that you must have performed the experiment. So this is how you should report it. The first one, I ensured that I avoided error due to parallax when taking the readings on the spring balance, which means I am going to be looking at the readings horizontally. I'm not going to bend. I'm not going to be looking sideways. I'm just going to look at the readings on the spring balance head on, horizontally, not from a slanting direction. Also, I made sure that the mass is totally immersed in water. You recall that in the question, there was a point where we were told to immerse the mass in water and also in liquid. So you ensure that the mass is fully submerged in water and then in the liquid. Also, you must ensure that the retor stand and the clamp are well tightened so that the spring balance doesn't fall off. And you also must ensure that the clamp is tightened and all set up in a horizontal position so that you can get the right readings on your clamp. As you can see on your screen, I ensure that the retor stand and clamp are well tightened. Also, you must ensure, you record that this way, I ensure that the mass is not touching the sides or base of the beaker. Also, I ensure that I correct zero error on the spring balance is another one. Also, I'm going to when I'm trying to immerse my solid into the water and into the liquid, I am going to avoid splashing. So I'm going to say I avoided splashing of water and liquid. And then lastly, I am going to say I repeated the readings so that I get accurate results. Another precautions you can state is that you have to first of all immerse in water, and then before you then immerse in the liquid. So which means you have to wipe off the water on the masses before you now immerse in liquid. So I'm going to say I wiped mass dry before dipping in liquid. So these are some of the errors we can avoid so that we get accurate results here. Moving on to the next question, we were told to state Archimedes' principle. Now, Archimedes' principle states that when a body is totally immersed in a fluid, it experiences an upthrust. Now, that upthrust here is equal to the weight of the fluid displaced. I'll give an instance. Let's say we have a fluid here. This is the volume. If we immerse mass M, Now, it suddenly appears as though the volume of the liquid had increased. No, that is not actually what had happened. What had happened is that those liquid occupying this portion, more like they are going to vacate this space in the liquid, and then they are going to move up. They're going to move up, so that by so doing, the mass M can occupy this space, then they move up. So what that means simply is that when you look at it, if this was V1, when I say V2 minus V1, that talks about, okay, the volume of liquid displaced. Now, the volume of liquid displaced, you need to know that it is equal to the volume of the mass M. Look, say that the volume of mass M is thrown off the liquid. The volume of this body is thrown off the liquid. We say it displaces its own volume of the liquid. So when we weigh the weight of this fluid displaced, the weight of this fluid displaced is what is called upthrust. So that is why we say upthrust is the loss in weight of a body. So the upthrust here is the weight of this liquid occupying this portion between V1 and V2. That is what the upthrust is. So Archimedes' principle is saying that when a body is totally immersed in a fluid, it experiences an upthrust. That's a loss in weight, which is equal to the weight of the fluid thrown off the fluid. That is equal to the weight of the fluid displaced. And that ends that. So moving on to the last question here, it says a piece of brass 20.0 gram, as you can see on your screen, is hung on a spring balance. We don't use we don't deal in grams in our physics. So we have to convert this to kilogram, and this is going to mean 20 divided by 1,000. This here is going to give us 0.02 kilogram. Okay. It says a piece of brass of mass 20 gram is hung on a spring balance from a rigid support, completely immersed in kerosene of density 8 times 10 raised to power 2. Okay. Let this be a beaker containing the kerosene. Okay, so we have this mass, so that let this be our brass. Now that we've immersed this, we expect that, okay, this should, the volume of the kerosene should appear as though it had risen. So what were we told to look for here? It says kerosene of density 8 times 10 raised to power 2. Determine the reading on the spring balance. So which means we're going to have, you know, this attached to a spring balance graduated already. Recall very well that density is equal to mass over volume. So since density is equal to mass over volume, then it means mass equals to density times volume. Since we are talking about, okay, we needed this mass to be in Newton, because our reading on the spring balance is going to be in Newton. So we talk of times acceleration due to gravity. So when we look at this, the fact that we are looking for the weight of the liquid displaced, the density here we have been given, the density of the kerosene we've been given as 8 times 10 raised to power 2. And of course, we have been given, we need to try and get first the volume of the liquid displaced. Now, the volume of liquid displaced is just equal to the volume of the brass. So what the first thing is, what is the volume of the brass? Volume of the brass, whenever we are looking for volume is actually mass divided by density. What is the mass of the brass according to this question? The mass of the brass is 0.02 divided by what is the density of the brass here? As you can see in that question, the density is 8 times 10 raised to power 3. 8 times 10 raised to power 3. This 0.02 here invariably means 2 times 10 raised to power minus 2. So if we compute this, this should give us the volume of the brass should be 2.5 times 10 raised to power minus 6 meter cube. So having said that, the next thing, now that we know the volume of the brass, it simply means that for us to get what the reading will be, so to get what the reading will be on the spring balance, the reading on the spring balance is going to be the weight of the fluid displaced here, and that's going to mean the density of the kerosene times the volume of the brass here. The volume of the brass here is the same thing as the volume of fluid displaced times volume of brass times acceleration due to gravity. So what is the density of kerosene? 8 times 10 raised to power 2. That is 8 times 10 raised to power 2. Times the volume of the brass is 2.5 times 10 raised to power minus 6 times 10. And that just converts it to Newton. So if we compute this, 8 times 2.5 times 10, 10 raised to power 2, 10 raised to power 6. So 8 times 2.5 is going to give us 20. 10 raised to power 2 plus minus 6, then plus 1. So this is going to mean 20 times 10 raised to power minus 4 plus 1, that's minus 3. And invariably, this is going to mean 2.0 times 10 raised to power minus 2 Newton. This here is our answer, 2.0 times 10 raised to power minus 2 Newton, or preferably we put this as 0.02 Newton. That is what will be our reading on the spring balance. And with that, we have come to the end. Remember, this question here is exactly or very close, at least 80% what your question is going to look like. And also sometime 2023, we had a question similar to this. The link to that particular lecture is going to be in the description of this video. That particular graph plottings and practical also dealt with relative density, so you can as well check up on that particular question, and I tell you, you cannot go wrong. From myself and the entire team, it's bye for now.